Hello and welcome to this week's lecture series for linear modeling. So far in all the past weeks we studied how to set up the finite element equation or the equilibrium equation in finite element method for any simple structure by making use of certain starting points. And using these certain starting points we set up a number of problems to get to the point of the Ku is equal to F equation. And now once this direct stiffness or this general equation including the stiffness matrix, the displacement vector and the force vector was set up, we could now think of those as building blocks for different elements, and if you put a number of elements together as different building blocks for a structure. So far we have considered everything in the truss format. That means we are looking at one-dimensional elements that were capable of stretching and compressing along its own axis. And we also considered these truss elements that can stretch and compress also in a 2D plane. That means they are lying at a certain orientation to a global coordinate system. So up until this point we have been able to pick up a certain element, get to the point of setting up the equilibrium equation, which is Ku is equal to F, and following that we were able to solve problems by putting all these building blocks together into a bigger problem, into a global problem, and then solving it for a solution. And the solution always consisted of the unknown, which is the displacements of a system under a certain loading condition. Now this week we will focus on beams. Beams are extremely versatile members. I know in the last video series I also said trusses are versatile because they can be used to build up a lot of structures, but there was a distinct limitation in trusses. So if you remember trusses, we considered them to be one-dimensional elements which were only capable of deforming along its axis. You could define it very easily by just using their material properties, the area of cross section and their length, and they could be loaded only at their nodes. So this was the problem of trusses. That means if you wanted a load to act, you always needed an associated point or node at which this load could act in the structure. If I wanted a load to act over here, we would have to attach a point or a node to this system. So this was the limitation of a truss. And that's what we can now get rid of when we consider beams. Beams are certain kinds of members that you have been dealing with for a very long time. That means you know a lot about beams, and one of the distinct features of beams that you may remember is bending. Bending is one of the most important characteristics of the beam. And how does that come about? How come there is a member that starts bending? Now if you remember, beams in general can have any cross section. So I'm just drawing a general section beam. You're looking at it from the side. So I have a certain section of a beam with its given length L, and instead of just having loads that are acting at the two ends, I can have loads that are acting throughout the length of the beam, and this is called a distributed load. It can be uniform, it can be varying, etc. But what happens because of this distributed load is that you can have more than just a single kind of load, as it was in the case of a truss. Now if I look carefully over here at the bending situation, then I have a distributed load, let's say W of x, because this is direction x. Then this load is changing. So if I find out its contribution at the two ends of the beam, then I can divide it as a single load here which is acting in this direction, and to compensate for the rest of the load that was acting everywhere across the beam, I can have equivalent moments. And because of these moments which are caused because of eccentricity of all these forces over here, my beam will now undergo a certain kind of deformation which is called bending. And this is the condition that trusses could not have exhibited. So therefore we are looking now at beams. So you will have different kinds of degrees of freedom that you will have to consider because of this particular nature of a beam. So in the first, the way the lectures will be set up today is that first we will consider a general beam theory. We will only consider one kind of beam theory, which is the Euler-Bernoulli. But make no mistake, you can also use other theories that are used for beams. For example, you can use Timoshenko beams for these conditions or for derivation of finite element equation. But we will only look at Euler-Bernoulli beams because you are also aware of it already, so it will go faster. But if you follow the steps, you will be able to use any theory for setting up beam elements. So first we'll do the general beam theory. Following the certain beam theory, we'll have certain results which will help us in setting up the basic stiffness matrix for a standard beam element. And I will tell you in a few minutes what a standard beam element actually is. And then after setting up basic stiffness matrix for a standard beam element, we will do basic stiffness matrix for a frame element, which is a advanced beam element, which will also be introduced to you in a few minutes. And finally, we will be able to set up a problem using these stiffness matrices and solve the Ku is equal to F problem to get a certain solution. So let's start first with the general beam theory. You can of course find some of this information back in the lecture notes, but I have not gone into a large amount of details using beam theory in the lecture notes because this is something that I expect you to know. But there are a lot of online students who may be missing some information, so we'll go through that very quickly in this video itself. So continuing, let's start talking about stiffness of a beam. Let's say I just want to discuss general Euler-Bernoulli beam theory. That's what I should call this section, Euler-Bernoulli beam theory. Now, Euler-Bernoulli beam theory enforces certain conditions in beams. And what is this? The most important condition that the Euler-Bernoulli beam theory follows is that we are only going to consider bending deformation. So I'm going to write here bending deformation only. So that's the only one we are going to look at, which means that you have a certain beam, like I showed you before. So you have a certain beam and there is a kind of a distributed load which is acting on it. And under this distributed load, you can have a sort of a bending of the beam. And what I want you to understand here is, of course, there will be a different kind of load acting because of the bending of the beam. So you'll have moments and forces. But what you need to consider, why this problem fits into the Euler-Bernoulli theory, is that let's consider that there is this small section in the beam, and you have this element ABCD. Okay, this small section is called ABCD, and once the load is applied on it and the beam bends, then you will of course have a deformation. Sort of looks like this, and there are new coordinates for A, B, C, D, which I'm going to dash. But what's really important here is that in the Euler-Bernoulli beam theory, if you had this plane AD, will always remain straight and perpendicular to the neutral axis, even after deformation. So if I make the neutral axis here and I bend it, my neutral axis therefore follows the curvature of bend, then this line here, the AD dash, is always going to be perpendicular and to this axis in its location, and it's always going to be straight. So there may be that it has a certain angle of rotation about this axis, but this axis has also the same angle of rotation to the global axis as it used to be from the reference axis. Now I can also pick out this little element and I can do a force balance. So I can say, okay, there was a certain load acting on it, which I can call W of x as I did before. And when I took out this element from this section, then there should be some surface tractions and moments that should be left behind to counter it. So if at this face I had I had this shear force V, and at this I have V plus dV, because there's a certain length I'm considering here to be dx, then there will also be a moment. If there's a moment m, then here there is a moment m plus dm. So this is the section of the beam under a distributed load. Now if I use all the different force moment equilibrium for the differential element that I have just drawn out, then I will be able to prove that the distributed load W is given as negative dV by dx. That means a change in the shear force V with respect to the length of the differential element dx will give us the load, or the distributed loading, which is defined in force per unit length. If I do, this comes out of a force equilibrium. So I'm just going to do a force equilibrium in the vertical direction. And if I do a moment equilibrium at the second point, or the point here, then I will be able to also prove that the shear force V is given as a change in moment with respect to the length of the differential element. So if you want to set up the final relation between the between the shear force and the moment and the distributed load, as well as the displacements of the element, you have to do a slightly more you have to do a few more steps, and I'll show you those as well in the next page. Let's start by drawing how would the beam actually deform. Okay, now I'm just going to draw the neutral axis of the beam, because then it's easy to visualize. So if I say this is the neutral axis of the beam and it has bent under a certain load, then the reference axis was somewhat here, and I have an angle at which this reference axis are now turned into the new axis. That means from a point it has you have a certain curvature in this beam. Okay, and this curvature is given as kappa, is given as 1 by rho, where rho is nothing but the radius of this curvature of this deflected beam. We can also so the curvature is actually given as 1 by rho, which can be defined as which is related to the moment as m by ei. So that is giving us the curvature of the beam. Also we know that there is a certain vertical displacement of this point, let's say. So the vertical displacement of this point is given as v of x, because it's going to vary along the length x of the beam. So the transverse displacement v, which is the vertical displacement in this case, is called transverse displacement, can also be related to the angle or the curvature for the for these angles given as theta. So we know that theta, or the angle of curvature, is given as the change in the transverse displacement per unit length. You can work this out, of course, it's quite simple. So if you have a small change in v with small change in x, then it's going to give you what is the angle theta when the angle is very small. So you can write this for small angles. So theta is given as dv dx. And the curvature for this angle, that means ka for kappa, the curvature, I'm going to write here curvature in case you forget. The curvature kappa is given as the second derivative of v. So this is the curvature of the slope, which is given as theta. So if I now equate equation 1 and equation 3, because this is equation 2, then I will get d square v dx square is equal to m by ei. Now we know from equation A, which was right here, so w is equal to minus dv dx and b is v is equal to dm dx, we can use both these equations over here now to say from, let's call this equation 4, from equation A we have w is equal to minus dv dx, and from equation B we have v is equal to dm dx, which implies that w is equal to minus d square m dx square. Now we know we have the d square m dx square, and we know from equation 4 the value of m in terms of ei d square v dx square. So we can write, in this case, we can say substituting 4 into, call this equation 5, we can write w minus w is equal to d square dx square into ei d square v dx square. Now if you have ei to be constant and only nodal forces and moments are working, that means there is no distributed load, then w can become equal to 0. So if w is equal to 0, then you have ei, when ei is constant, d4v dx to the power 4 is equal to 0. So this is of course one of the very important conclusions or results that you see in Euler-Bernoulli beam theory, where you have related the moments and the shear force and the distributed load to the material properties and the curvature and the displacement of the beam. Now considering that we now know sufficiently enough about the mathematical formulation of beams and bending that's happening in beam, we will be able to set up the element type for the beam property and then follow through to make the stiffness matrix.